Your car's engine might be running smoothly right now with no check engine light glowing on the dashboard, yet a tiny, overlooked sensor could be secretly robbing it of power, forcing it to guzzle more fuel, and gradually wearing down its lifespan. The surprising part? This happens without any obvious warning. How is it possible for one small part, barely larger than a fingertip, to cause sluggish performance, higher gas bills, and even emissions failures all at once? Experienced mechanics encounter this scenario constantly. Customers bring in vehicles that feel weak and inefficient. Technicians replace spark plugs, swap out coils, or even point fingers at the fuel pump, yet the issues persist. The real fix often comes only after cleaning a sensor that hardly anyone suspects. And no, it's not the one most drivers immediately guess. There's a hidden troublemaker that slowly collects grime over time, feeds incorrect information to the computer's brain, the ECU, and turns a strong engine into one that constantly underperforms. In this breakdown, we'll examine the most problematic sensor step by step. The one that causes the biggest headaches, rarely gets any maintenance attention, and can dramatically revive engine performance in just minutes will be revealed last. Number 8, the MAF, mass airflow, sensor. In today's fuel-injected engines, the mass airflow sensor plays an absolutely vital role, yet it's frequently neglected. Its primary task is to accurately detect the exact amount of air entering the engine, down to the gram. It achieves this through an extremely fine platinum hot wire, thinner than a strand of hair, that's kept at a steady high temperature by electric current. When incoming air rushes over it, the wire cools down proportionally to the volume and velocity of the flow. The ECU calculates air mass by measuring how much extra current is required to maintain that constant heat. Trouble starts when tiny contaminants, like road dust, oil mist from the PCV system, vapors from aftermarket oiled filters, or everyday city pollutants, build up on that fragile wire. This layer alters its heat transfer properties, leading the ECU to receive false readings. Common consequences include reduced throttle response and lost horsepower during strong acceleration, mysteriously higher fuel usage, erratic idling that fluctuates without reason, and occasionally stalling when lifting off the gas abruptly. Interestingly, diagnostic data from repair facilities shows that about 40% of cars throwing lean or rich mixture error codes don't have a defective MAF, they're just dirty. The correct fix involves using a specialized aerosol cleaner designed specifically for MAF sensors, applied carefully without ever touching the delicate element. Number 7. The MAP, Manifold Absolute Pressure, Sensor. Many engines, particularly those using speed density fuel management, rely on the manifold absolute pressure sensor instead of a MAF. This device doesn't measure airflow directly, rather, it detects pressure changes inside the intake manifold via a piezoresistive chip that varies its resistance based on vacuum or pressure. During idle with a closed throttle, strong vacuum produces low pressure readings, usually 20 to 30 kilopascals. At full throttle, vacuum drops dramatically, and pressure climbs toward atmospheric levels, around 100 kilopascals at sea level. The ECU then uses this pressure data, along with air temperature and RPM, to compute air mass through established gas laws. Issues commonly arise from aging vacuum lines that crack, harden, or loosen slightly. Even the smallest leak throws off the readings, making the ECU think the engine is under heavier load than it actually is, which triggers overfueling. Drivers notice excessive fuel smell, poor mileage, dark exhaust smoke, and recurring rich condition trouble codes. In many American auto shops, thoroughly cleaning the sensor's mounting port and replacing or repairing those vacuum hoses resolves around 80% of cases originally attributed to a faulty sensor. Number 6. The oxygen, O2, sensor. When it comes to keeping combustion clean and efficient, oxygen sensors are the ECU's real-time feedback system in the exhaust stream. They continuously monitor leftover oxygen to help maintain the perfect air-fuel balance, making thousands of tiny adjustments every minute. The core is a zirconia ceramic element that must stay above 300 degrees Celsius to produce voltage based on the oxygen difference between exhaust gases and ambient air. At the ideal 14.7 to 1 stoichiometric ratio, output hovers around 0.45 volts, lean conditions drop it below 0.3 volts, while rich conditions push it over 0.6 volts. The ECU watches these quick voltage swings to fine-tune fueling instantly. Contamination is the biggest enemy. Substances like silicone from sealants, phosphorus from oil additives, or lead traces from bad gasoline can coat and poison the sensing surface. This slows reaction time and degrades accuracy, leading to delayed corrections, wasted fuel, reduced power, rough running, and almost certain failure on mandatory emissions tests in regulated areas. Number 5, the TPS, throttle position sensor. Mounted right on the throttle body, the throttle position sensor acts as the driver's direct voice to the ECU, reporting precisely how far the accelerator pedal is pressed. It works like a variable resistor, potentiometer. A wiper slides along a resistive track, splitting a reference voltage from roughly 0.5 volts at closed throttle to about 4.5 volts at wide-open throttle. This signal helps the computer decide between economical cruising and full power delivery, adjusting fuel and spark accordingly. Over time, carbon buildup, where on the track, or dirt creates flat spots where voltage suddenly jumps or drops. These glitches often happen at everyday throttle angles, like light cruising or gentle tip-in, resulting in hesitation, surging, jerky acceleration, or brief power cuts at certain pedal positions. In severe cases, the engine may even cut out completely. Technicians spot this by graphing live TPS voltage on a scan tool while smoothly sweeping the throttle, watching for any abrupt changes in the otherwise linear signal. Number 4, the crankshaft position sensor. No modern engine can run without a reliable crankshaft position sensor. It essentially gives the ECU its sense of timing and speed. Positioned close to a toothed wheel on the crankshaft, it produces electrical pulses each time a tooth passes its magnetic pickup. These pulses allow the computer to track exact piston locations and RPM, enabling perfectly timed fuel injection and ignition sparks. Debris such as metal particles from normal wear, baked-on oil residue, or general road grime can coat the sensor tip, weakening or distorting the signal. Symptoms range from random misfires and hard starting to unexpected stalling when hot, extended cranking times, or momentary loss of spark while driving. Surprisingly often, a simple cleaning of the sensor face using electrical cleaner and a soft cloth brings back rock-solid performance in engines previously suspected of major ignition or injection problems. Number 3, the ECT, engine coolant temperature, sensor. This sensor functions as the engine's core temperature gauge, providing the ECU with constant updates on whether the motor is ice-cold, in the process of warming, or fully up to operating temperature, typically around 90 to 100 degrees Celsius. That single reading drives a cascade of decisions: richer fuel mixtures for cold starts to prevent stalling, elevated idle RPM during warm-up to reduce emissions and wear, activation of electric cooling fans once things get hot, and optimized spark advance based on thermal expansion and knock resistance. It's foundational to engine management. Without accurate ECT data, the computer is essentially flying blind on thermal conditions. Faults emerge when the sensor tip collects coolant deposits, when terminals oxidize from moisture exposure, or when internal elements drift due to age-related corrosion or thermal cycling. The ECU then misinterprets the engine as either perpetually cold, triggering constant enrichment, or falsely hot, leaning out the mixture dangerously. Drivers experience skyrocketing fuel use, cooling fans that never kick in, leading to gauge spikes and potential head gasket damage, difficult hot restarts with flooding or hesitation, erratic idle surges, and random overheating episodes that seem unexplained. A critical reminder for maintenance: focus primarily on the electrical connections rather than the probe immersed in coolant. Always perform this with a fully cold engine to avoid pressurized coolant spray and burns. Identify the sensor, usually screwed into the cylinder head, thermostat housing, or a large coolant passage. Gently release the connector clip and pull it free. You'll frequently discover green verdigris corrosion, white mineral deposits, or oily film on the pins and harness side. Spray dedicated electrical contact cleaner liberally on both sides. For tougher buildup, use a soft nylon brush or a cotton swab lightly dampened with cleaner, never force or twist pins. If removing the sensor itself, For thorough inspection, drain a small amount of coolant into a catch pan first, then replace the sealing O-ring or washer to prevent leaks. After cleaning, allow full drying, reconnect until the tab locks securely, and top up coolant if needed. If installing a new sensor, apply thread sealant sparingly. A restored ECT signal means precise cold/hot fueling, timely fan operation, accurate timing adjustments, and the end of those puzzling symptoms that point everywhere except the temperature data the ECU relies on. Number 2, the IAT, intake air temperature, sensor. Think of the IAT as the engine's air density monitor. It tracks whether incoming air is cool and oxygen-rich, requiring more fuel for proper combustion, or warm and expanded, needing less to avoid over-rich conditions. This data integrates with MAF/MAP readings to refine air mass calculations, ensuring optimal mixture across seasons, altitudes, and driving styles. When dirt, oil film from PCV blow-by, or intake debris coats the sensing element, readings skew, often reading artificially high or low, and performance suffers. The engine feels flat and unresponsive, particularly on chilly mornings. Fuel economy tanks as the ECU compensates with incorrect injector pulse widths, acceleration lags because density corrections are wrong, and drivability becomes weather-dependent, with good days and bad ones that defy logic. In many vehicles, the IAT is built into the MAF assembly, but in others it's standalone, threaded or clipped into the air intake duct, manifold, or throttle body, strategically placed to sample pre-combustion air. Cleaning demands precision and gentleness. With the engine stone cold, locate the 2-wire connector, release the lock, and disconnect without yanking wires. If removable, unscrew or unclip it carefully. The heart is a small thermistor bead or exposed resistor, highly fragile and sensitive to mechanical damage. Never use abrasives, tools, or high-pressure air, that ruins it immediately. Instead, apply sensor-safe or electronic contact cleaner in short bursts directly on the element, allowing runoff to carry away grime. For heavy fouling, a ultrasoft artist's brush or swab, damp, not soaked, can lightly wipe, zero pressure, no residue left behind. Air dry fully for several minutes, reinstall with any gasket intact, and snap the connector back until it clicks. A spotless IAT lets the ECU compute true air density, adapt fueling to real-world conditions, smooth out cold/hot transitions, and banish the random rough running that owners often chase with fuel additives, plugs, or mystery repairs. Number 1, cleaning electrical terminals and connectors. This is the absolute game-changer that too many overlook, far more impactful than buying expensive sensors or fluids. Pristine new parts, top-tier oil, and fresh plugs mean nothing if signals degrade through corroded, contaminated, or loose pins. Every wire harness and plug is the nervous system of the ECU. A bit of oxidation, trapped moisture, or a backed-out terminal can create ghost codes, flickering lights, and symptoms that come and go unpredictably. The highest return service? A systematic connector cleanup. With the ignition off and battery disconnected if possible for safety, target the big hitters, MAF, MAP, TPS, IAT, ECT, crank/cam sensors, O2 sensors, and any others in the harness. Proceed sensor by sensor, depress the locking tab, wiggle free the connector, never tug wires, and peer inside. Green corrosion, black soot, oily residue, or pushed back pins. That's your problem source. Flood both male and female sides with electrical contact cleaner, tilt to drain, and repeat. Stubborn sulfate or dirt yields to a plastic bristled brush or swab, gentle strokes only, preserving alignment. Dry thoroughly, compressed air on low or just time. Apply a thin film of dielectric grease to the rubber seal, not the contacts, for moisture protection in exposed areas. Reassemble until the click confirms a firm mate. This thorough pass eliminates phantom intermittence, erases false codes, stabilizes erratic behavior, and often revives engines that just feel off without any part replacement. It's the foundational step that makes everything else work reliably. Do it once, and save hours of diagnostic guesswork.
Thanks for watching. Don't forget to like, comment and subscribe for more videos. See you in next one.